Hello, today we're going to talk about reactivity 3.2.5 and 3.2.6, which really gets into electrochemical cells, and then we will get specific with voltaic cells. Okay, so electrochemical cells are what we call redox reactions effectively. But there's two main types. And the first one is voltaic cell. The other one is called an electrolytic cell. And I'm going to just kind of very briefly introduce both of those here, and then we'll get more specific later on. But voltaic cells are also called galvanic cells, and they are spontaneous. They generate electrical energy. Electrolytic cells, on the other hand, are non-spontaneous. They consume electrical energy, which means that they need some kind of power source to make them work. Now, in a voltaic cell, you're going to have an anode and a cathode. And the anode is where oxidation occurs. Remember, oxidation is losing electrons. The cathode is where reduction occurs. And reduction is where it gains electrons. Then in a voltaic cell, we label the anode the negative electrode and the cathode we label the positive electrode. Electrolytic cell, we also have an anode and a cathode. The anode is still where oxidation occurs. And don't forget that oxidation still means that it's losing electrons. Cathode is still reduction, which is gaining electrons. But in an electrolytic cell, the anode is the positive electrode. And the cathode is the negative electrode. So the way that I remember this, anode is always with oxidation because they're both vowels. Cathode is always with reduction. Those are both consonants. I also remember that anode is like anion. So anode, very similar to anion, which has negative charge. And I remember that voltaic cell, it matches. So the anode, which is like an anion, matches the charge. Cathode, which is a positive ion, like a cation, matches the charge. And then for some reason in my brain, I'm able to remember that electrolytic cell, the charges are just opposite of what they normally are. Okay, so let's get a little bit more specific with voltaic cells. We're going to focus our attention on primary cells, which effectively means that the materials get used up. In a later section, we'll talk about rechargeable cells, which is a little different than this. So voltaic cells, typically you're going to see diagrams where they have two separate chambers, and one of them will represent the anode and the other will represent the cathode. And each chamber would be a half cell. So the whole thing is a cell, each part of that is a half cell. The electrode is typically a piece of metal, and the pieces of metal are connected by a wire. Very often that wire will go through a voltmeter or like a multimeter. It's something to measure the voltage that goes across. You also need something called a salt bridge. And I'll label this as well, voltmeter. Now, so this is your general setup. Sometimes you'll see a variety of different ways that you could set up the voltaic cells. Sometimes instead of like two separate beakers, it'll be like the same container, but it'll have like a porous bridge in between them instead of a completely separate salt bridge. But this is a good representation of what's going on overall. Now, let's talk about what these things are made up of. So you have your metal, and let's go ahead and call this the anode, and we'll call this one the cathode. But be careful, the anode is not always on the left. I'm just happened to put it this way. And this is your metal. Whatever metal you have on one side, you should have, I'm going to call this one, let's call this metal X and this one metal Y. So whatever metal you have on the anode, solid, you should have metal ions within the solution. And then whatever metal you have on the cathode side, you should have the same metal ions in the solution. Then you're going to make sure your salt bridge has salt on it. A lot of times we'll use some kind of alkali metal salt. You could use something like potassium nitrate is a common one. The reason for that is because the anode is where oxidation happens. The cathode is where reduction happens. And the oxidation is where it loses electrons. So electrons will leave here and go across towards the cathode, which is where the metal is gaining the electrons. Okay. So if the electrons are being lost from this side, it's a slightly positive charge. It becomes unbalanced in terms of charge. So the negative ion of your salt is going to travel toward that solution to balance the charge. The positive ion will travel toward the cathode to cancel out the excess electrons that are traveling toward that side. So you have this like balance going on because of the salt bridge. And you will notice if you ever build one of these, if you take out the salt bridge, nothing will happen. You won't be able to read a voltage anymore because the charge has to be balanced for the reaction to continue. Okay, so let's go ahead and draw a real version of this. So in one beaker, I will say I have a piece of copper metal. And then in the solution, I have, let's say I have something like copper sulfate, which of course is soluble, so it breaks down into copper ions and sulfate ions. And so your solution is a bluish color because of those copper ions. Now, it's connected to our other half cell, which let's say it's zinc. So this is a piece of solid zinc, and in my solution, let's say I have zinc nitrate. Which is soluble, so of course it breaks down into zinc ions and nitrate ions. Now zinc solution is neutral, so zinc solution is colorless, so you won't have that, you won't be able to see a whole lot that's going on, but there's our two half cells connected now. Now if you were to attach this, of course, to a voltmeter, right now you would not see anything because there's no salt bridge. So I would need to add a salt bridge. Now in this situation, the copper is going to act as the cathode and the zinc will act as the anode. And so the zinc metal will be oxidized and turn into zinc ions and release electrons. And those electrons can travel through the wire toward the copper electrode. The zinc that dissolves into ions is just going to remain in the solution there. But because you're generating more of these positive ions, your negative ion in the salt bridge, whatever that happens to be, is going to come in here to balance out those excess zinc ions. Now at our cathode, we're having reduction happening. So the copper ions that are in the solution are going to gain the electrons from the zinc to form copper metal. So that means these copper ions are going to turn into solid copper, and they kind of stick to the copper electrode when they get the extra electrons. And so since we're using up positive ions, I need to regenerate those positive ions with our salt bridge, so the cation is going to travel towards the cathode. You need to be able to represent this type of setup. You need to know the direction of movement for the ions in the salt bridge, the direction of movement for ions in the solution inside the half cells themselves, what's happening to the metal electrode, the size of the metal electrodes, the direction of movement of the electrons. Basically everything about this diagram you really need to know well. So one way that we can represent the Voltaic cells without drawing out the whole setup is using what we call a cell diagram. And the general structure of that looks like this. It's a solid, and then the aqueous version of that solid, and then two lines, aqueous, solid. And so effectively you have your reactants and products of your anode half reaction on the left, and then your reactants and products of your cathode reaction on the right. And so because anode is for oxidation, it's losing electrons when it does this reaction here, loses electrons. The cathode will be gaining electrons, reduction, for that half reaction. So each part of this is a half reaction, and the whole thing adds up to our total cell. So if we're going to write one for the zinc and copper cell that I drew on the previous page, the zinc was our anode. So we had our solid zinc, which lost its electrons to form zinc ions in the solution. In our cathode, we had copper ions in the solution, which were gaining the electrons to form extra solid copper. And so that's a cell diagram. Okay, so let's look at this example, which connects this concept of voltaic cells back to activity series, which we've talked about with single replacement reactions. So it says to predict which of the following will be the anode and which will be the cathode when the half cells are connected. We've got zinc and then iron. So if I were to use an activity series, I would see that zinc metal is slightly more reactive than iron. So that means the zinc is more likely to displace the iron ions in whatever salt. So remember that we always list it as just the ions, but there's some kind of salt going on there. Maybe it's iron chloride or iron nitrate. But we remove the spectator ions from the diagram. So because zinc is more reactive, this reaction is what will proceed, and you will be left with zinc ions and solid iron because the zinc replaces it. So if I were to write this as a cell diagram, I would have the solid zinc forming zinc 2+ ions, and then I've got my iron ions in the solution, and then solid iron being formed. And of course, this will be the anode, and this is the cathode. Okay, so then for this example, we have said, it says, predict what would be observed if an iron spatula was left overnight in a solution of copper 2 sulfate. So that means I have some solid iron being left in a solution of copper 2 sulfate. Well, I know that the sulfate is going to be a spectator ion. I just need to double check with my activity series to see whether the iron will be able to displace the copper. Now the iron is more reactive, it's higher up on the activity series, so this reaction can proceed. I'm going to go ahead and eliminate the sulfate as a spectator ion there, and we will form iron 2+ ions and solid copper. So that's the reaction that would happen. But this doesn't say what we would actually observe. So you would see that the copper 2 sulfate solution is a blue solution, and the iron metal is, iron colored. It's like a dark grayish as a solid. Then as this reaction proceeds, the blue solution will be going away. You will start having an iron solution forming, which can be like in the yellow-orange range. And you will be forming some of this solid copper, which is a brownish, reddish solid. So what you will visually observe is that the iron spatula is dissolving, forming a more of a yellow-orange solution. The blue solution is not turning blue anymore. It's getting less blue and becoming solid copper. Typically, the solid copper will be kind of attaching to the spatula. It almost looks like it's rusting, but it's not rust. Remember that rust is Fe2O3, which we're not forming rust. We are forming solid copper. Okay, so electrical energy can be derived from the combustion of fossil fuels or from electrochemical reactions. What are the similarities and differences in these reactions? So electrochemical reactions that produce energy are the Voltaic cells, right? Combustion of fossil fuels can also produce energy. They're both redox reactions. So combustion is always a oxidation reduction reaction because the oxygen that has to react starts at an oxidation state of 0 and changes over the course of the combustion reaction. Now, many times with combustion reactions, it involves a release of heat energy, and then you'll need some kind of generator to change that heat energy into electrical energy. Whereas if you just have a Voltaic cell, which could be part of a battery, it's just going to produce that electrical energy, and you can use it as it is, which is really interesting. So that's kind of a difference between the two.